Hi everyone. In this presentation, we are going to talk about the data augmentation approaches for NLP. So what is data augmentation? Data augmentation encompasses methods of increasing training data diversity without directly collecting more data. It has received active attention in recent machine learning research in the form of well-received general-purpose techniques. Why data augmentation is important for NLP? Due to off-the-shelf availability of large pre-trained models, there are increasingly more tasks and domains to explore in NLP. Many of these are low resource and have a paucity of training examples. So data augmentation can play an important role in creating many use cases. An ideal data augmentation should be both easy to implement and improve model performance. The distribution of augmented data should neither be too similar nor too different from the original. Let's look at the rule-based techniques. Wei and Zhou propose an easy data augmentation. It is a set of token-level random perturbation operations, including random intersection, deletions, and swap. They solve improved performance on many text classification tasks. Unsupervised data augmentation proposed by Xie show how supervised data augmentation methods can be exploited for unsupervised data. Automatic paraphrase dataset augmentation using graph theory. For paraphrase identification, Chen constructs a side graph over the data, with individual sentences as nodes and pair label as side edges. They use balance theories and transitivity to infer augmented sentence pairs from the graph. Motivated by image cropping and rotation, Sahin and Steinman propose dependency tree morphing. For dependency annotated sentence, children of the same parents are swiped and some deleted. This is most beneficial for language family with rich case-making system. The rule-based techniques is easy to implement but usually offer incremental performance improvements.
There are two classes of example interpolation techniques. One class of data augmentation techniques pioneered by MixUp interpolates the inputs and labels of two or more real examples. This class of techniques is also sometimes referred to as mixed sample data augmentation. Another class of extensions of MixUp, which has been growing in the vision community, attempts to fuse raw input image passed together into a simple input image, rather than improve the continuous interpolation mechanism. Examples of this paradigm include cut-mix, cut-out, and copy-paste. A bottleneck to using MixUp for NLP tasks was the requirement of continuous input. This has been overcome by mixing embedding or higher hidden layers. SQ2 MixUp generalized MixUp for sequence transduction tasks in two ways. The hard version samples a binary mask and picks from one of the two sequences at each token position, while the soft version softly interpolates between sequences based on a coefficient. The soft version is found to outperform the hard version.
So the third technique for data augmentation is model-based. The baseline model is mostly sequence-to-sequence or language model, pre-trained RNN or transformers. Normally, we modify part of the component for the model, like the decoder part, to generate the diverse new paraphrases of the input text. We also have cases like we can replace words with other words that generated by the recurrent new language model under current context. We can also generate example using a pre-trained transformer and then select the most informative and diverse set. Another way is to use masking technique applied in BERT you mask the word position and reconstruct it to unmask them. You can also adjust the overall semantics to fit the new word's context by replacement entity. And you can estimate a generative process from training set directly and then sample from it instead of given a phrase or a sentence and build the data augmentation from the specific example. We can estimate a generative process from training set directly. We also have document level paraphrasing and model-based techniques combined with other simple DA techniques.
Low-resource languages are an important and challenging application for data augmentation, typically for neural machine translation. Techniques using external languages such as WordNet may be difficult to use effectively here. There are ways to leverage high-resources languages for low-resource languages, particularly if they have similar linguistic properties. They use back translation and self-learning to generate augmented training data. Inspired by work in computer vision, Faded generate additional training examples that contain low-frequency words in synthetically created contexts. Qin presents a data augmentation framework to generate multilingual code switching data to fine-tuned multilingual BERT. They see improved performance across 5 tasks with 19 languages. Zhao attempts to mitigate gender bias in core reference resolution by creating an augmented dataset identical to the original, but biased towards the underrepresented gender and trained on the unions of the two datasets. CDA is proposed for gender bias mitigation, which involves casual intervention that break association between gendered and gender-neutral words. Musavi increases training sentences with their corresponding predicate argument structures, improving the robustness of transformer models against various types of biases. Fixing classes imbalance typically involves a combination of undersampling and oversampling. One is smart. It generates augmented minority class examples through interpolation, which still remains popular. Another one is multi-label smart. It modifies smart to balance classes for multi-label classification, which classifiers predict more than one class at the same time. Other techniques, such as EDA, can possibly be used for oversampling as well. Data augmentation methods can ease few-shot learning by adding more examples for normal classes introduced in a few-shot phrase. Several methods are applied only on image tasks, but their theoretical formulations are generally applicable. Adversarial examples can be generated by using innocuous label-preserving transformations, such as paraphrasing. It follows state-of-the-art NLP models. Specifically, they add sentences with disruptor spans to passages to construct AVs for span-based QA. Zhang construct AVs for paraphrase detections using word swapping. Kang and Glockner create AVs for textual entailment using WordNet relations.
The first talk is summarization, which is about extracting or abstracting keywords from the document. The DA methods applied for it, including back translation, which is like you first translate the input to another language and then you translate it back. And you have a consistent loss for keeping the augmented data with the original one to be invariant related to the loss. Another one is iterative DA, which is a mix of synthetic data generated from the common crawl dataset. It's basically you train a reverse system to generate text from summary, and then use it as synthetic data. And the third one is to create two training data by modifying CNNs or daily email resources. And it's about context query answer triples using simple entity detection and some anomaly methylation algorithms. The second task is about the Q&A. For the Q&A DA methods, first is also the back translation. Second one is you can leverage the question generation model to produce augmented example. Third one is about passage retrieval. So you basically use the Q&A pairs to feed into the passage, and then you find the answer in the passage. And for next example, you say we find those set without answer instance. And the other one is substitute part of text with other language, or you can use the logical and linguistic knowledge to generate additional training data. The third task is about sequence tagging task. So it's about if you have a sequence of words, I want to tag each word. It's like name, entity recognition, or something like that. And the first method for this is DAGA, two-step DA. First, the language model is trained using a sequence of text and words and linearized. And then you have a sequence and sample from this language model and linearize to generate a new text. And you use this pair as input for augmented examples. The second one is sequential mix, which is you mix the token and the latent representation by token level interpolation. This is similar to the linear interpolation, but this is a discrete case, so we have token level interpolation. The next task is about parsing. Parsing tasks are mostly related to the SCFG, which is synchronized context-free grammar. Most often it is induced from the training data. And along with a generative model, you can sample the new examples and then add it back to the training set for diversity. You can also generate a synthetic question SQL pair for the parsing task using the SCFG. Another way is you basically replace part of the original examples with other parts that have similar context, or the dependency tree morphing, which is about replace words with other words of the same POS, or morphological features, or dependency labels. The next task is grammatical error correction, and this is mostly about correct wrong grammar in a passage. We can make use of additional resources like explore multitask transfer, use other tasks annotated data, or we can use an example is use German's edits from Wikipedia revision history and use those relating to GCE for the augmented data. Second method is to add synthetic errors to noise the text. And the general way is you can add some noise to the data. For example, you can generate a confusion set by a spell checker and then add those confusion elements to the text. Another way is you learn the error pattern from the small annotated samples along with the POS specific noising. So this is mostly related to the POS tag. And the third way is to improve the diversity of generated errors by adding noise to the latent space. Next is neural machine translation. So this is about translating the language. two methods is used. First is masking for original data. You can mask with random other words from vocabulary or related words, or you can use a context mixture of multiple related words. You can also add more data by using the output predictions from the model already learned. Next is data-to-text NLG. This task is about generate natural language description for the structured or semi-structured data inputs. A common example is the gain summary. And in this example, we perturb the game score without changing the overall game outcome. And this will be an invariant part for the augmentation. And we can also permute the input sequence and inject Gaussian noise to the decoder, and then sample the examples from it, and use a self-training strategy to use those examples. Next is the open-ended and the conditional generation. This is mostly about the text generation problem. The general approach is replacement and add some synthetic noise, random insertion, and then semantic text exchange. So the details is mostly about replace it with a synonym or hypernym or hypername. And you can also insert some random words or use semantic related words to exchange. Also about the task for dialogue, mostly it's the same for from the previous approach. We use word span and the sentence level DA methods. And we can also construct augmented phrase training examples based on dialogue state and act labels, which is unique for the dialogue case. We can also propose an RL-based DA approach for the dialogue state tracking, which is also unique for dialogue tasks. Another way is to introduce a graph-based representation and then use it for DA by creating the new dialogue path. Last is about multimodal task. This is a task about we not only have the text for NLP text, we also have speech, image, and audio for other format of data. And the typical way is you can use cross-modality meshing network to produce the synthetic image text pairs. We can also use synonym replacement and the contextualized word embeddings for the image caption problem. We can also have question generation and adversary examples for the visual QA problem. Last is about
There are still many challenges in data augmentation for NLP. For example, dissonance between empirical narrative and theoretical narrative. There appears to be a lack of research on why data augmentation works, so we cannot predict the performance of data augmentation in NLP, and minimal benefits for pre-trained models on in-domain data. With the popularizations of large pre-trained language models, it has come to light that a couple previously effective data augmentation techniques for certain English text classification tasks provide little benefits for models already achieve high performance on in-domain text classification and multimodal challenges. Many rules focus on augmenting a single modality or multiple ones separately. And for specialized domains, for those with domain-specific vocabulary and jargon, for example, medicine, many pre-trained models and external knowledge cannot be effectively used. Data augmentation becomes less beneficial when applied to out-of-domain data, likely because the distribution of augmented data can substantially differ from the original data. And low-resource language. It presents similar difficulties as specialized domains. And for the offline and online data augmentation, in computer vision, standard techniques are typically done stochastically. allowing for data augmentation to be incorporated in the training pipeline. In NLP, however, it is unclear how to include a language code module to apply data augmentation stochastically. This is because data augmentation techniques for NLP often leverage external resources that are not easily transferable across training pipelines, and lack of unification is a challenge for the current literature on data augmentation for NLP. With some of the challenges, new opportunities for future work arise. For example, for the pre-trained models on in-domain data, further work could try to find which data augmentation is likely to be effective for large pre-trained models. For multimodal, further work could try to explore simultaneous image and text augmentation for image captioning. There will be more version-inspired techniques. Although many NLP data augmentation methods has been inspired by analogous approaches in computer vision, there is potential for drawing further connections. For self-supervised learning, we can explore how to effectively manipulate text for both pre-training and downstream text. For the offline and online data augmentation, we can try to find a language code module to apply data augmentation stochastically. And we can work on good data augmentation practice. For example, unify benchmark tags, datasets, and frameworks or libraries. Making code and augmented dataset publicly available. Reporting variation among results, and have more standardized evaluation procedures.